Download this code from codegive.com, link in the description below. OK, let's dive deep into process synchronization, a crucial concept in operating systems and concurrent programming. I'll cover the problems, solutions, common techniques, mutexes, semaphores, condition variables, and provide C++ examples to illustrate. The need for process synchronization. In a multi-programming or multitasking environment, multiple processes or threads can execute concurrently. While this concurrency improves system efficiency, it also introduces challenges when these processes need to share resources, like files, memory, or even hardware devices. If not carefully managed, this sharing can lead to data corruption, inconsistent states, and other undesirable outcomes. Race condition. A race condition occurs when the outcome of a program depends on the unpredictable order in which multiple processes access and modify shared data. The final result becomes uncertain and can change on different executions. Critical section. A critical section is a code segment where a process accesses shared resources, variables, data structures, files, etc. The key requirement is that only one process should be allowed to execute its critical section at any given time for a specific shared resource. 2. Requirements for a good synchronization solution. Any solution aiming to solve the process synchronization problem needs to fulfill these key criteria. 1. Mutual exclusion. Only one process can be in its critical section for a shared resource at any given time. This is the most fundamental requirement. 2. Progress. If no process is in its critical section, and some processes want to enter their critical sections, only those processes that are not in their remainder sections can participate in deciding which will enter its critical section next. This ensures that processes don't indefinitely block each other from accessing the resource. 3. Bounded waiting. There's a limit, a bound, on how long a process has to wait to enter its critical section. No process should be blocked indefinitely, preventing starvation. 4. Portability. Optional. Ideally, the synchronization mechanism should be easily portable to different hardware and operating system platforms. 3. Common synchronization techniques. Let's explore the common techniques for achieving process synchronization. 1. Mutexes, mutual exclusion locks. Concept. A mutex is a synchronization primitive that acts like a lock. It has two states, locked and unlocked. A process must acquire, lock, the mutex before entering its critical section and release, unlock, it when exiting. If a process tries to acquire a mutex that's already locked, it's blocked until the mutex becomes available. Implementation. Mutexes are often implemented using hardware support, atomic instructions, or kernel-level synchronization primitives. C++ example, using std mutex. Explanation. Std mutex mtx, declares a mutex object. mtx.lock, acquires the mutex. If another thread holds the lock, this thread will block until the mutex is released. mtx.unlock, releases the mutex, allowing another waiting thread to acquire it. std thread, creates threads that concurrently execute the increment_data function. t1.join, t2.join, waits for the threads to complete their execution. Important. Always ensure that you unlock the mutex, even in the presence of exceptions. Use RAII, resource acquisition is initialization, techniques like std_lock_guard or std_unique_lock to automatically release the mutex when exiting a scope. The std lock underscore guard ensures that the mutex is automatically unlocked when the lock object goes out of scope, example when the function returns or an exception is thrown. This prevents deadlocks due to missed unlock calls. Std unique underscore lock is more flexible, allowing deferred locking, timed locking, and transfer of mutex ownership. 2 Semaphores asterisk. Asterisk concept asterisk. A semaphore is a more general synchronization tool than a mutex. It's an integer variable that can be accessed only through two atomic operations. Asterisk wait, or p, for proberen in Dutch decrements the semaphore value. If the value becomes negative, the process is blocked until the value becomes non-negative. Asterisk signal, or v, for verhogen in Dutch increments the semaphore value. If there are processes blocked waiting for the semaphore, one of them is unblocked. Asterisk types asterisk. Asterisk binary semaphore asterisk. The semaphore value is either 0 or 1. It's essentially equivalent to a mutex. Asterisk counting semaphore asterisk. The semaphore value can be any non-negative integer. It's used to control access to a limited number of resources. For example, a database connection pool with 5 connections could use a counting semaphore initialized to 5. Asterisk C++ example, using std counting underscore semaphore, C++ 20 and later, or manual implementation. Since std counting underscore semaphore is a relatively recent addition to C++, many compilers and standard libraries don't fully support it yet. If you're using an older compiler, you'll need to either use a third-party library or implement a basic semaphore using a mutex and a condition variable. See the condition variables section below for an example. Here's an example assuming std counting underscore semaphore is available. Asterisk explanation asterisk. Asterisk std counting underscore semaphore 5 semaphore, 5, creates a counting semaphore with an initial value of 5. This represents 5 available resources. Asterisk semaphore.acquire, attempts to acquire a resource. If the semaphore value is greater than 0, it's decremented, and the thread proceeds. If the value is 0, the thread blocks until another thread releases a resource. Asterisk semaphore.release, releases a resource, incrementing the semaphore value. This might unblock a waiting thread. Asterisk the code creates 10 threads, but the semaphore only allows 5 to access the resource, simulated by std this underscore thread sleep underscore for, concurrently. 3 condition variables asterisk. Asterisk concept asterisk condition variables are used to allow threads to wait for specific conditions to become true. They work in conjunction with a mutex. They provide a mechanism for threads to efficiently wait for a signal from another thread, without busy waiting, repeatedly checking a condition. Asterisk operations asterisk. Asterisk wait, mutex, atomically unlocks the mutex and puts the thread to sleep, blocks it, until it's notified. When the thread is woken up, it reacquires the mutex. Asterisk notify underscore 1, wakes up one thread that's waiting on the condition variable. Asterisk notify underscore all, wakes up all threads that are waiting on the condition variable. Asterisk C++ example, using std condition underscore variable. Asterisk explanation asterisk. Asterisk std condition underscore variable CV, declares a condition variable. Asterisk std unique underscore lock std mutex lock, mtx, uses std unique underscore lock because std condition underscore variable wait requires it. Unique underscore lock is more flexible than lock underscore guard. Asterisk CV wait, lock, return data underscore ready, the consumer thread waits on the condition variable until data underscore ready becomes true. Critically, this atomically unlocks the mutex while waiting, and reacquires it when woken up. The lambda expression return data_ready, is a spurious wake-up guard. Condition variables can sometimes wake up spuriously, without being notified. The lambda ensures that the thread only proceeds if the condition is actually true. *CV notify_1, the producer thread signals the condition variable, waking up one of the waiting consumer threads. *Y condition variables are essential for implementing more complex synchronization patterns, such as *producer-consumer problems, where one or more producers generate data and one or more consumers consume it. *readers-writers problems, where multiple readers can access shared data concurrently, but only one writer can access it at a time. 4. Common synchronization problems. 1. Deadlock. A deadlock occurs when two or more processes are blocked indefinitely, waiting for each other. Conditions for deadlock, Kaufman conditions. Mutual exclusion. Resources are held in exclusive mode, only one process at a time can use a resource. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. No preemption. Resources cannot be forcibly taken away from a process holding them. Circular wait. There exists a set of processes P1, P2, Pn such that P1 is waiting for a resource held by P2, P2 is waiting for a resource held by P3, and Pn is waiting for a resource held by P1. Deadlock prevention. Breaking one or more of the Kaufman conditions can prevent deadlocks. For example, avoid hold and wait, require processes to request all required resources before starting execution. Allow preemption, if a process holding a resource requests another resource that cannot be immediately allocated, release the held resource. Impose a total ordering on resource requests. Deadlock avoidance. Use algorithms, like the banker's algorithm, to dynamically allocate resources in a way that avoids circular wait conditions. Deadlock detection and recovery. Allow deadlocks to occur and then detect them. Recovery can involve terminating one or more processes or preempting resources. C++ example, deadlock. This code will likely deadlock because thread 1 acquires mutex 1 and then tries to acquire mutex 2, while thread 2 acquires mutex 2 and then tries to acquire mutex 1. This creates a circular wait. Avoiding deadlock. To prevent the deadlock, you could ensure that both threads acquire the mutexes in the same order. Example, always acquire mutex 1 before mutex 2. C++ also offers std lock to lock multiple mutexes atomically, all or nothing. 2. Starvation. A process is repeatedly denied access to a resource, even though the resource is available. This can occur if the scheduler gives preference to other processes, or if the synchronization mechanism has unfairness issues. Causes. Priority inversion, unfair locking mechanisms. Solutions. Priority inheritance, temporarily boost the priority of a lower priority process holding a resource needed by a higher priority process. Fair locking mechanisms, ensure that processes acquire resources in a fair order, example using a queue-based locking mechanism. 3. Priority inversion. A high priority process is blocked by a lower priority process. This can happen if the lower priority process holds a lock needed by the higher priority process. The priority inheritance protocol, mentioned above, is a common solution. V. Other synchronization mechanisms, briefly. Spin locks. A type of lock where a process repeatedly checks, spins, to see if the lock is available. Spin locks are efficient when the lock is held for a very short time and the cost of context switching is high. However, they can waste CPU cycles if the lock is held for a long time. Typically used in low-level kernel code. Read-write locks. Shared exclusive locks allow multiple readers to access a resource concurrently, but require exclusive access for a writer. Useful when reads are much more frequent than writes. Monitors high-level synchronization construct that encapsulates shared data and the operations that access it. Monitors provide mutual exclusion and condition variables. Many languages provide monitor-like constructs, example synchronized methods in Java. Message passing processes communicate and synchronize by sending messages to each other. No shared memory is directly accessed. Common in distributed systems. 6. Choosing the right synchronization technique. The best synchronization technique depends on the specific requirements of your application. Mutexes for simple mutual exclusion. Semaphores for controlling access to a limited number of resources or for signaling between threads. Condition variables for more complex synchronization scenarios where threads need to wait for specific conditions to become true. Read-write locks when reads are much more frequent than writes. Message passing for distributed systems or when direct shared memory access is undesirable. 7. Important considerations. Atomicity ensure that operations on shared data are atomic, indivisible. Hardware support, atomic instructions, is often used to implement atomic operations. Memory barriers, fences in multi-threaded programs, compilers, and CPUs can reorder instructions for performance reasons. Memory barriers prevent these reorderings and ensure that memory operations are performed in the intended order. Necessary for correct synchronization in some cases. Testing and debugging. Concurrent programs are notoriously difficult to test and debug. Use tools, like thread sanitizers, to detect race conditions, deadlocks, and other synchronization errors. Carefully design your code and use appropriate synchronization mechanisms to avoid these problems in the first place. This comprehensive tutorial covers the essential concepts of process synchronization. Remember to practice with different synchronization techniques and explore more advanced topics to become proficient in concurrent programming. Good luck.